Okay, hello and welcome back, everybody. Moving on to the last section in the first chapter of the book, functions, inverses, and equations. You probably feel somewhat confident about all three of these, but as with everything else in this chapter, it's good to cover it again, make sure we're all in the same place before we move back toward calculus. On top of that, I actually had a different definition of a function than maybe you've been introduced in the past, and this really is the mathematical definition of a function. The one that we tend to learn in high school is a little bit different. So when we say that we have a mathematical function, the domain, which you've heard of, should actually always be included in the definition of the function itself. I know there were a lot of questions, in high school algebra courses that looked like find the domain of f of x. You can have something like 1 over x squared minus 3x plus 2, for example, and you would figure out where's the denominator equal to 0, and maybe you would factor the denominator as x minus 2 and x minus 1, and you say, oh, the domain is, the real numbers minus the points 2 and 1, or maybe you would write that like to 1 union 1 to 2 union 2 to infinity. But in reality, you shouldn't have to ever find the domain of a function. It should be given to you. I know that feels strange with what we've been talked about. This idea of finding a domain is really find the maximal subset of the real numbers that could be the domain. That's what they were trying to say, but it's such an annoying thing to say that they were never saying it, and it was really just a practice to see if you could recognize when things divide by 0, which is a very useful thing to recognize. But in reality, functions should always be paired with domains from the beginning. So as far as this book is concerned, we will be seeing functions paired with the domain from the beginning. We'll never have to find them ourselves. And then there's this other word, codomain, which you probably haven't heard before, and instead you heard the word range. But in fact, the range is a subset of the codomain. Sometimes it can be the entire codomain, but the codomain is just kind of some like other place that it's going to send numbers inside of. You could think about like Middlebury College is a codomain, but maybe Carr Hall in Middlebury College is a specific range. It's a specific subset of the codomain, and maybe a function only puts you into Carr Hall rather than the entire Middlebury College. So think about codomains as like this larger area that functions have the ability to place things into, but they don't necessarily have to find everything in the codomain. And then there's a rule, which this rule is what most people think of as a function, what most people mean when they say function. Because a rule is kind of this statement. It's that f of x equals something. So in reality, every time we talk about functions, we're going to say f, and then we're going to list a domain, an arrow, a codomain, we'll say defined by, and then we'll provide the rule for everybody. So, that earlier example of f of x equals 1 divided by x squared minus 3x plus 2. This was really just the rule of the function and not the function itself. The function itself is paired with a domain and a codomain. So that's my little extra 2 cents on how we're going to think about functions. It really is 98% of the time okay to think about the function and the rule as the same object, but you'll see I like to be precise about things, and so give some examples of numerical functions. At least I got f r to r, so you get an example. I'm listing the real numbers as the domain, and I'm listing the real numbers as the codomain. This just means these are two sets that the function takes as an input and puts as an output. And here we have x squared minus 2x plus 2. And so you'll see if I can actually factor this really quick as x, what would it be, x minus 1 squared plus 1. So you'll see that this is actually the range of this function is the smallest it can possibly get is the positive real number 1, and then it can get up to infinity. So the range of f is actually this interval 1 to infinity, but I've listed the codomain as the entire real line. So the range is a subset of the codomain in this case. In our second setting, I say, well, we have functions that could map, two-dimensional numbers to two-dimensional numbers. So that function is going to have 2 inputs, and it has 2 outputs. They're just separated by a comma, and that's perfectly well defined as well. We just have like a domain, which is R2, and a codomain, which is R2. The domain and the codomain don't always have to be the same, but in this case they are. We can also have complex functions, h going from c to c, and there's my complex variable. Let's say I take the exponential of I times the complex variable plus log of, you'll recognize that as the norm or magnitude, squared of the complex number plus 1. So this is a perfectly well-defined function for which every input that's a complex number will give me an output that is also a complex number. And then finally, we do see a case where the domain and codomain are different. The domain here is only the natural numbers as a domain, but the codomain is all of the integers. And what we have here is our rule says you take a natural number, we're going to take -1 to that power, and then we're going to take n squared plus 1 and multiply by it. And we'll get integers rather than natural numbers out of that. I did want to include some cases of real-world functions because, once again, I like to stress that even though we use numbers a lot of the times in math, they're not the only things we can kind of consider math as being able to touch. Math is able to handle situations that don't necessarily only consider numbers. So here we've got a red light filter, which we're going to place over different colors of light. We can consider the act of filtering light as a function. So the domain of the function is going to be the possible colors of light. The codomain is going to also be possible colors of light, and we can represent the function, which is the filter, and the red filter, right, red light filter, as, well, what does it do to the input x? Well, if x is red and I put a red filter over it, then I'm just going to get red out of it. But if the input light is blue and I put a red filter over it, then I'll get purple. If the input light is green and I put a filter over it, I actually won't get any light. You'll notice if you wear like red tinted glasses, anything that appears green without the glasses on immediately appears black, or at least very dark, because there's very little red light that can make its way through. And in this case, you can think about like I've written the function as f, which maps the domain possible colors of light to the codomain possible colors of light. And it's defined by this is a piecewise function, but I actually haven't included any numbers in this function, for example. So it's just something that giving us the ability to talk about like real world actions as mathematical functions allows us to apply our intuitions of math to the real world, which is quite useful. Another case, we could think about an oven set to 350 and the act of baking as a function. So I'll name my function b, which maps the domain possible doughs cross r plus. What do I mean by this? I'm saying not only do I have possible doughs, but I'm also including positive r, as in times we bake. So whatever amount of time we bake something for, r plus being the positive real numbers. So I'm going to take both of those as an input. And it looks like I forgot my codomain, but we can map the codomain to baked goods. So if baked goods is my codomain, then what do we have going on over here? Well, b of whatever sort of dough I input along with an amount of time is going to give me bread, so long as I put bread dough in and I bake between 25 and 35 minutes. It's going to give me cookies if I put cookie dough in and I bake between 12 and 20 minutes. By the way, it would give me charcoal if I put anything in and I bake longer than 3 hours. You get the idea. You can represent like actions, real world actions and operations as functions. And you can think about composing, adding, and performing operations on these functions that aren't necessarily just with numbers. Another example, I've got a car which obtains an estimated 28 miles per gallon. We can consider the car itself as a function which has a domain of possible volumes of gasoline and a codomain of possible miles traveled, right? So we can write C, the car, as mapping possible volumes of gasoline into possible miles traveled. We can just define it by C of x equals 28x, because the total number of possible miles will just be 28 miles per gallon, and it's going to be taking the gallons of gasoline and multiplying them by 28. So that one is a little bit numeric. It's like pseudo-numeric, and this is where we're getting into the realm of pseudo-mathematics as opposed to just English and or just mathematics. So you have this kind of operating area where you have both. That's kind of nice. And we also have, maybe if you're a microbiologist in the group, polymerase chain reaction machine, which basically doubles the amount of DNA you have in a situation. So in this case, if you have a specific number of polymerized base pairs of DNA, as your domain, the codomain is also this number of polymerized base pairs, and the function p just takes that number and it doubles it, right? If I run a PCR machine once on polymerized base pairs, then I would double the total number of base pairs, which is represented as 2n. We can think about running multiple cycles of a PCR machine as adding a second variable, right? So maybe if I have, this is the number of base pairs, this first variable, but the second variable is maybe the number of cycles we've run, then we can think about this as, well, it's a function from 2 inputs of natural numbers to a single output of natural numbers. It's going to look like what? Well, every time it runs a cycle, it multiplies by 2, so we'll get 2 to the power of cycles we've ran multiplied by the number of base pairs we started with. And this can actually be represented as a composition of functions, right? Because if we repeat a process over and over again, that's the same as composing functions. So with that said, if you've forgotten what composing functions are, that's actually our next topic. So our next definition is going to be composition of functions, which basically says this is why it's important that we have our domains and codomains from the beginning. So we have something like f, which maps a to b, and g, which maps b to c, right? We need to kind of be explicit about that codomain being that domain. And the moment that the codomain of the first function lines up with the domain of the second function, we can compose the two. And compose just means you're going to run the first function on an element, run f first, and then you run g on output. So that's all it is to compose, but of course if I had swapped the order here, if I tried to run something like f compose g, which by the way would have the definition f of g of x, well, let's think about where g of x ends up, it ends up in the codomain of g, which happens to be c in this case. Well, if c is not the same thing as a, suppose they're not the same, then f sees it and it has no idea what to do with it. So that's you can only compose in specific directions sometimes. Like the next example, for example. So we've got f, which takes natural numbers to real numbers, and g, which takes real numbers to complex numbers, where f is going to take a natural number, add 1, and take a square root. G is going to take a real number, it's going to multiply it by e to I times that real number. So you can think about composing g with f as well. It's going to be g of f of n, and f of n we know is the root of n squared plus 1. And we're just going to grab whatever that output of f is. This is the output of f, and there it is right up there. And we're going to plug it into g, right? Plug it into x for g, so that x and that x are going to be the output of f. There's that x, and there's that x. So this makes perfect sense to go g of f. You can imagine if I tried to go in the opposite direction, technically it kind of still works. It's just that I'm am requiring that f's domain is a natural number. So because g doesn't necessarily give me a natural number, it's just I'm not gonna consider it if I tried to compose in the other direction. As a real world example, let's think about a solar panel which produces 0.3 kilowatts while the sun's shining, an attached air conditioner which can cool a house by 1 degree Fahrenheit per hour for each 0.1 kilowatts it uses. We can consider the solar panel as a function whose domain is hours of sunlight and whose codomain is kilowatt hours. Similarly, we can consider an air conditioner as a function whose domain is kilowatt hours and whose codomain is degrees Fahrenheit cooled. They can be represented mathematically as well. Here's my solar panel, which takes positive hours of sunlight to positive kilowatt hours, and it's going to take, the air conditioner is going to take positive kilowatt hours to positive degrees cooled. Each of them are defined by, well, the solar panel makes 0.3 kilowatts for each kilowatt hour, but in this case 0.3 times hours, right? It's going to give me my kilowatt hours, and then the air conditioner is going to take the energy input and it's going to divide it by 0.1 and ask how many degrees Fahrenheit it actually is able to cool, right? So the composition of these two functions, you can think about actually hooking, right? If I've got my solar panels over here, what do they look like approximately? They kind of look like a funky looking grid. So there's my solar panels. And suppose I just literally wire these up to my air conditioner. There's my AC unit. If I actually hook them up to each other, that is the composition of functions, right? I'm composing these two functions. The first one takes in sunlight. I've got sunlight over here and it's beaming down on the solar panel. It takes in sunlight, outputs electricity. So I've got sunlight coming in, electricity coming out. Well, the AC turns that on its head and says, oh, I'm going to grab the electricity in and I'm going to output some nice cooling. Brr. So the fact that we compose, kind of like these middle terms cancel out, we have sunlight which transitions into cooling. That's kind of the act of composition. And of course, in this case, if I were to compose the two, I'm looking at A, and then I'm going to plug the 0.3 T in for E inside of A, and we simplify and we find out that if we hook them together, we can cool at 3 degrees Fahrenheit for every hour of sunlight we get. And so the mathematics just kind of comes for free once you decide to compose functions. But you should really think about it as compose, like it's a real world composition that directly translates into the composition of functions, and the mathematics comes for free. That's the way I like thinking about it. So composition of functions gives us an immediate foray into inverse functions because they can only be defined as compositions. The point of an inverse function, if I look at the domain and the codomain of my original function f, the inverse has to swap the two of them around. So if I'm going a to b for f, the inverse has to go from b to a. And the way it's defined is that, and it's notated by this superscript -1, by the way, the way it's defined is that the composition of a function and its inverse have to cancel each other, right? So they're just going to cancel each other, which means the output of the composition is just x. And this occurs in both directions. So they cancel each other, the output is just x. So I like to add this remark because this is a very common mistake students will make, and that's that inverses are not reciprocals. We use the same notation, the superscript -1, for both inverses and reciprocals, but just keep in mind the power -1 only applies to numbers. Right, and since functions are not numbers, the functions are actions, right? So functions take something in and they output something. So because functions aren't numbers, they should always be paired with like an input, right? Every time you see f inverse, you should have an input next to it. So you should be able to recognize it as not a number. The inverse only means reciprocal when it comes to numbers. When it comes to functions, inverses and reciprocals are not the same thing. So don't get something like, if I say f of x equals cosine x, I don't want to see somebody say f inverse of x is 1 divided by cosine x. This is not true. And it does happen every semester, multiple times. So just do your best to not do it. It's not the end of the world, but it's always something to make sure that you're aware of before you start. Okay, so let's look at an example of an inverse function. We're just going to look at this as an example, not necessarily to calculate it, but just to verify that we actually have an inverse function. So here's a function which maps 1 to infinity to 1 to infinity, so that's your domain and codomain. The function is defined by x squared minus 2x plus 2. Keep in mind we've factored this already as x minus 1 squared plus 1. The inverse function here happens to be defined by root x minus 1 plus 1. And you can kind of see how they mimic each other after we do factor it, but we're going to pretend we don't actually know how to find the inverse yet. I'm just going to verify, let's verify that this is an inverse. And the way we verify that it's an inverse is just by the definition, right? Because the definition says if I compose the two, I should end up just with x in either direction. So I'm going to go ahead and compose the two of them in either direction and cross my fingers, I end up with x. So in the first case, I'm going to put f on the outside and the inverse on the inside, which means I'm going to grab this entire term and I'm going to plug it in for both of these instances of x. And what that looks like is there's my x squared term, there's my single x term, and then I'm going to simplify. So to simplify, I do have to FOIL this first piece. There's going to be my first, my outside, my inside, and my last terms from foiling. And then if I simplify a little bit, the square and the square root can cancel. Why does it not become an absolute value, you may ask? Because this is, once again, in most cases, you have to be careful about absolute values. Well, it's because my terms are always positive, right? Absolute values don't matter as long as things are always positive. So thankfully, everything's positive here, so I can cancel those nice and safely. And that term's going to be x minus 1. We've got a couple terms on the inside that are going to cancel. There's going to be a 2 root x minus 1 and a negative 2 root x minus 1 that cancel, as well as a plus 1 sitting around, but we'll also have a minus 2 and a plus 2 that cancel. But this plus 1 that's sitting around will cancel with that minus 1, and we're left with exactly x. So that's verifying the inverse from one direction, but we can also verify from the other direction by doing f inverse of f of x, which if I go to the top here and think about composition, if I'm composing f into f inverse, I'm going to grab that entire piece and plug it in for x in the lowercase. Right here, plugging it in for x in the lowercase, we simplify what's inside the square root. That plus 2 becomes plus 1. That ends up being a perfect square, which will cancel. Here's the absolute value sign again, but keep in mind everything is positive, so we can drop it, cancel the 1s, and we end up with just x. Another example of a lovely inverse would be the function g mapping from r to the positive real number, 0 to infinity, and its inverse mapping the positive real numbers to all of r, the original function given by e to the x cubed, and the inverse given by log x to the 1/3 power. Notice the 1/3 is outside of the parentheses. I can verify inverses yet again by looking at g of g inverse, which means I'm going to take log x of 1/3 and plug it in for x up here. That means it's going to go in for x up in the exponential. The powers 1/3 and 3 cancel, and then the e and the log cancel, and I'm just left with x. If I run that in the other direction, we've got g inverse of g of x, where if I jump back up to their definitions, if g is on the inside, I'm going to take this, I'm going to plug it in for x, and then I'm going to see the log and the e cancel, so I'll just have x cubed to the 1/3, and the 3's cancel, and I'm left with x. One more nice example, a pretty tricky one actually. This is one that a lot of people study in abstract algebra class. The function h, which maps the natural numbers to the integers, which is defined piecewise. Well, I'm going to divide it by 2 when n is even. I'm going to take 1 minus the number and then divide it by 2 when n is odd. What this actually does, if I lay my natural numbers out here, I have 1, 2, 3, 4, 5, and so on. Well, it takes the odd numbers, it's going to subtract 1 from 1, and then divide by 2, that's going to give me 0. It's going to take 1 minus 3 is negative 2, divided by 2 is negative 1, 1 minus 5 is negative 4, it's going to divide it by 2, I'm going to get negative 2 out of that. My even numbers just get divided by 2, 2 goes to 1, 4 goes to 2. What we would see out of this is that actually every single integer would be found, because they're at 0, 1, negative 1, 2, negative 2. I would end up with 3, negative 3 for the next 2, and so on. It would give me every single integer. So this is kind of a quaint function that maps the natural numbers to the integers. And its inverse is defined as an input of the integers. What does it do to the integers? Well, if the integer happens to be positive, it's just going to double it. And if the integer happens to be negative, it's going to take 1 minus doubled it. And that will send me right back to where I started. The work to verify that this takes you back where it started is a little bit messy, but we can do it piece by piece. If I'm looking at h composed with h inverse, that means I'm going to plug h inverse into h. So I'm going to plug this entire term in for n here and in for n here, as well as this one and this one. And when I do that, I just go ahead and write out the cases. It would only be the 2n case when n is positive, so that's the only case that would go in the top term, and it would be like the 1 minus 2n case when n is negative would be the bottom term. And then I go ahead and simplify everything. You would see that both terms end up being n, no matter if I'm even or if I'm odd, and so a function which is piecewise equal to n everywhere is actually equal to n overall, and recall n is our original variable here. The reverse is kind of similar. You don't have to fully understand this last example. It's just kind of a quaint case where we're not dealing with real numbers anymore, but we're dealing with integers. So while these examples give us some insight to verifying that we have found inverses, the way that we would actually find them, if somebody asks us to find an inverse function, is through the process of solving equations. And so we're going to take a quick foray into solving equations, and then we'll get back to finding inverse functions. With that said, I want to dissect the word equation because I think a lot of people will use the word equation without knowing exactly what it means. They'll refer to like functions as equations, they'll refer to formulas as equations, and a lot of these mathematical objects that feel equation adjacent aren't actually equations. What an equation actually is, if I dissect the word, it's equa, meaning equality, and shun, meaning object of. So we're really looking at an object of equality, or in other words, the definition I have here, an equation is a mathematical equality containing at least one unknown variable. And so once you set up an equality like x squared minus 4 equals 17, now it's an equation. If I just say x squared minus 4, that's an expression. If I said something like x squared minus 4 equals f of x, not really an equation because this is trying to define the function f of x. So, keep in mind, equation, try to save its use only when you're referring to equalities where there's an unknown variable that you would wish to solve for. Now, the solution to an equation is going to be a specific definition of that unknown variable under which that equality is actually true. So if I had something like my x squared minus 4 equals 17, and I said something like x was equal to plus or minus root 21, that's really a definition here at the end. Under this definition, x equals plus or minus root 21, the bottom equation holds true. So let's look at an example of an equation that maybe doesn't consider numbers. Once again, I like to harken back that math doesn't necessarily have to consider numbers. If we think about a computer which displays colors as a combination of red, green, and blue light, we can create the equation red plus unknown equals magenta, whose solution, if I jump down a little bit, happens to be the solution blue, right? Because we know that red plus blue light actually gives us magenta light. And so that's how equations can work, but of course numerical equations are much more useful. With that said, once again, this is a bit pedantic of me, but I like to say that equations are really the only mathematical objects that can be solved. We will often say that problems are solved. That's fine, but I wouldn't say that you shouldn't say that you should solve an integral, x squared dx to say that this is equal to x cubed over 3 plus c. That's not solving an integral. It's maybe computing an integral or evaluating an integral or simplifying it or something. So try to use the word solve only when you're referring to equations. We also have systems of equations. And systems of equations are just like multiple groups of equations with multiple unknowns in them that need to be solved simultaneously, right? And I think you've seen these before, where maybe this is another example of light. I've got red plus an unknown equals unknown 2, and then cyan plus an unknown 2 equals unknown 1. You would find out that the solutions, which need to satisfy this at the same time, we've got unknown 1 is equal to green and unknown 2 is equal to yellow. So once you have the double definition of the unknowns in the equations, you've found a solution. Now, numerical equations are kind of the ones that we're actually used to. These are equations where the values of the elements are themselves number systems, and our favorite number systems that we've seen, at least in this course, are NZ, Q, R, and C. But there are actually some very interesting number systems that we won't get into in this course that if you continue in math, you may eventually discover. But of course, your basic algebra solves numerical equations for you. So something like 3x plus 7 equals -5, we're going to subtract 7 from both sides and divide by 3 to recover x equals -4 as our solution. Or the quadratic formula, which I wanted to put somewhere in this section just in case we didn't forget it. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. You'll have to forgive me for my singing. But that is, the quadratic formula, which we always love to use. Here's a quadratic equation, right? So when people say equation, look, it's equal to 0. Formula solves the quadratic equation. So it provides a solution to the quadratic equation. And we can solve this above 1, x squared minus 2x plus 2, using the quadratic formula, and we end up with 1 plus or minus I. Now, where did that plus or minus I come from? Because we do have the ability to work with complex numbers now. Let's plug everything in. If I'm looking at the coefficients here, I have a 1 for A, a -2 for B, and a 2 for C. So I'm going to plug 1 in for A. There's the 2 spots for A. I'm going to plug -2 in for B, -2, -2 for B, and I'm going to plug 2 in for C. And then I'm going to simplify, and in particular, it's right here. If I simplify, I get the square root of -4, and this is where we need complex numbers. Because the square root of -4 is equal to the square root of -1 times the square root of 4, but the square root of -1, right, if I have I squared is -1, then the square root of I squared, also known as I, or the square root of -1 is I, so we call this I times the square root of 4, or I times 2, so there I've replaced root -1 times root 4 with a 2, and then I decided to simplify to end up with 1 plus or minus I as the solution to this quadratic equation. We can also solve like rational expressions, right? So this rational expression, what would we do here? We would multiply both sides by x minus 3, and that would cancel on the left-hand side. So we'd have x minus 3 is 7x minus 21, and then simplify a little bit more, pull the 3's to the right and the 7x's to the left. We get -6x is -24, and divide by -6, and we find out that x is equal to 4. So that's all going way back to algebra that I hope feels very straightforward. We do, however, have an example of solving a cubic equation here, because these do show up periodically, and I want to make sure we know how to at least attempt to solve the cubic equation. So here's a cubic equation, a little bit tricky, probably something you analyzed in Algebra 2, but probably not something you necessarily remember how to solve from Algebra 2. Well, we have a few choices. The first is that a cubic formula does exist, so I've provided a link to the cubic formula here. It's really ugly, and you probably don't want to use it. Nobody's really asking you to use it. A computer can use it, but that's about it. In other words, if you ever have a cubic equation that needs to be solved, it can be factored. No professor is going to give you a cubic equation that needs to be solved that cannot be factored. And so the best way to factor any polynomial is to find its roots, right? And so we're actually going to find at least one solution to this equation first, and then we're going to divide by x minus the first root, because all polynomials can be factored, x minus a, x minus b, x minus c for some a, b, and c. And so if we know one of these roots, which would be a, b, or c, we can divide everything by x minus a, and that would cancel those terms, and we're left with a quadratic at that point. And then we could use the quadratic formula. So in this case, we're going to guess maybe a small solution, and we're just going to try some solutions out, and then once we find one of those, we're going to divide by x minus the first root, and that should recover a quadratic for us. So in this case, let's guess -2, -1, 0, 1, 2, and there's me plugging all 5 of those in and just evaluating. And what we see is that actually both -2 and +1 are roots. So -2 and 1 are roots, which means that this original cubic is divisible by x minus -2, or it's divisible by x minus 1. But for now, let's just take x minus -2 as a divisor of this polynomial, and let's go ahead and divide it. So here I'm doing polynomial long division. I'm going to take my cubic, and I'm going to divide it by x minus -2, my first root. And if you've forgotten how to do polynomial long division, let's forget about our answer here. What do we have to do? Well, I've got my cubic term here, and I've got an x term there, and I need to multiply that x term by some coefficient to recover the top term of the cubic. Well, how do I get 3x cubed out of x? I have to multiply it by 3x squared. And once I do that, I get, a 3x cubed here, and I get a 6x squared here, but I'm going to subtract those off, and that's perfectly going to cancel the first term. I'm going to be left with -4x squared as my second term. But then I'm going to have to come up with something to cancel -4x squared, so I'll have to multiply by -4x. That's going to give me a positive 4x squared, but -4x times 2 is going to give me -8, so plus 8x. And then I'm going to add these two terms together. I'm going to get a positive 1x, and there's going to be the 2 left over from the beginning. So positive 1x with the 2 left over from the beginning is exactly what I had from the beginning, so I'll have a plus 1 sitting around. So 3x squared minus 4x plus 1, notice if I erase everything, 3x squared minus 4x plus 1 is the resulting quadratic. So that means that I've found my first solution, which was -2, and then I divided out by that root, and that gives me this new quadratic 3x squared minus 4x plus 1, which now I can just go ahead and use the quadratic formula on, which says my solutions are 2/3 plus or minus 1/3, which is just 1 or 1/3. So my 3 roots are the 1 here, the 1/3, and the -2 I've already divided out. So if we scroll all the way down, I realize I talked far too much about this, but that's just to make sure that it's clear how we find these. We have 1, 1/3, or -2 are the solutions to our cubic. We also want to know that we can actually solve systems of equations if we remember how to do these. The natural way that I always do it is just with this method called the substitution method. And I've got a step-by-step case here for you on how to use the substitution method. We're going to solve any of the equations for one specific variable and then remove that equation from the system. Then we're going to plug in what the variable must be equal to from the first case, because we solved for it, into each other instance of that variable. That action has to remove that specific variable from all of the remaining equations. Now you're going to have a system with one fewer equation and one fewer variable, which we can repeat with 1 and 2 until there are no more unknown equations or variables. And at the very end, you're going to have one variable which has to be given a numerical value. And then you can kind of reverse directions from that point, because you found one with a numerical value. The previous cases will be equal to some version of that with the numerical values. So let's go ahead and follow those steps for this particular system of equations. And to do that, what am I going to do? I'm going to grab my first equation. I'm going to solve it for, in this case, I'm going to solve it for x. If I solve that first equation for x, it tells me x has to be -1 minus 2/3 y. And then I'm going to remove that first equation from my system, and I'm only left with this equation, at which point in step 2, I can actually grab this and plug it in for x in the second equation. And when I plug it in for x in the second equation, I recover the bottom right equation, which does need to be simplified. It's a little bit of work, I'm going to go ahead and simplify this equation. And when I do, I FOIL out the squared term and grab like terms together and then pull everything to one side so it looks nice. You get the following, right? This bottom right quadratic in the variable y. We can actually use the quadratic formula on this equation, and we recover that y has to be either 2 or negative 1/2. Now that we know y is equal to 2 or negative 1/2, recall at the end of the first step, I found out that x was equal to some version of y. Well, if y is either negative 2 or y is equal to 1/2, then I can actually figure out what x is equal to as well. So in the very last step, I have my cases of, well, when y is equal to 2, then x is equal to negative 7/3, or if y is equal to negative 1/2, x is equal to negative 2/3. And so we have our first set of solutions here, negative 7/3 and 2, and our second set of solutions, negative 2/3 and negative 1/2. Now that we're more comfortable solving equations, we can actually talk about how we would find inverse functions. And basically, we find inverse functions by recognizing that f of x equals y is an equation. Right? If I write it as f of x equals y, it is an equation which is solved by x equals f inverse of y. And so recognizing this understanding is going to give me the ability to find inverse functions. I'm basically going to solve a specific function equal to y for x, for example. And so the proposition I have here is finding inverse functions, which basically says, given a function which maps a to b, defined by some expression involving x, we may obtain the inverse by following our step-by-step process, which is interpret the function as equal to y so that we actually have y equals some expression of x. Then we exchange the roles of x and y. So now we have x equals some expression involving y. Then we're going to solve that later equation for the unknown variable y. And then the solution to the equation has to be phrased as y equals some new expression involving x. And then we interpret y equals f inverse of x, which is the actual inverse function. This is exactly what we've done before. This is my long-winded approach to saying swap x and y and solve for y to find the inverse function. So let's actually do that here. If I have something like f of x equals 2x minus 3 cubed, to do the inverse function, I'm going to replace y on the left-hand, or f on the left-hand side with a y. I'm then going to swap x and y around, and I'm going to solve for y. So to solve that equation for y, I have to take 1/3 of both sides, power 1/3 of both sides. That's going to be x and 1/3 is 2y minus 3. And then I'm going to solve for y by adding 3 to both sides and dividing by 2 of both sides. We get y is 1/2 x to 1/3 plus 3/2. Or in other words, if I replace that y with f inverse, we say f inverse of x is 1/2 x to 1/3 plus 3/2. Second case of computing an inverse, to make our lives just a little bit harder, we're going to compute the inverse of the function f of x equals x divided by x squared plus 1. We're making our lives harder because this will end up being a quadratic when we are inverting the function. So we're going to replace the f of x on the left-hand side with a y, and then we are going to end up swapping x and y around. So we have this expression, and now I'm going to solve this expression for the variable y. But to do that, you would recognize I have to multiply both sides by y squared minus 1. So that comes up to the left. I've got x times y squared minus 1, which will give me xy squared minus x equals y. And if I rearrange this, it seems a little bit strange, but if I rearrange this to the following, xy squared minus y minus x equals 0, I can actually use the quadratic formula on this equation to solve for y, because we recognize that the coefficient on y is an x, but that's just playing the role of a. Coefficient on the y term is a -1, that's playing the role of b, and a negative x is playing the role of c. So if I put x in for a, -1 in for b, and negative x in for c into the quadratic formula, I actually end up with this expression, which does solve for y. So y ends up being 1 plus or minus the square root of 1 plus 4x squared all over 2x. Well, that means that that's what f inverse has to be, right? F inverse is 1 plus or minus the square root of 1 plus 4x squared all over 2x. Except, one very special part here is we can't have plus or minus in an inverse function, right? We can't get away with that plus or minus inside of an inverse function because you can't get two numbers out of one function. You need to get one number out of one function. So we have to be a little bit clever. And ask the question, is it the plus case or the minus case that matters? Well, there's one way to check if it's the plus or minus case that matters, and this is where the domain and codomains of functions actually become important, because I know if my original function was defined as -1 to 1 mapping into R, that means that the inverse has to flip the order of these, so it starts with R and it ends up with -1 to 1, or in other words, my plus or minus has to be chosen so that the answers I get lie in the range -1 to 1. If I go back to f inverse, and I look at my plus minuses, how do I tell which one ends up in the range -1 to 1? Well, let's just try it on a couple points. If I try it on the point 1, I plug all those numbers in, and I get 1.618 when it's the positive case, and I get 0.618 when it's the negative case. Well, 0.618 is in negative 1 to 1. 1.618 is not in negative 1 to 1, so we definitely want the minus sign, and so we go ahead and keep the minus sign, and that's how we find f inverse using a quadratic formula. So that's all I've got. We're moving on to exercises now. It's been a long one. Thanks for hanging in there with me. I know this is kind of like the hard version of your Algebra 2 course, but it's good practice. We're getting better at some of the trickier things that maybe we didn't fully understand in Algebra 2. Anyway, I'll see you in the next video. Bye.